Everyone, I'd like to begin by thanking the organizers for inviting me here, and I think it's early but not premature to say that this is going to be a successful conference. I'd like to talk about spectral properties of small Hadamard matrices, and this is joint work with Dora Dukai and John Hauserman at the University of Central Florida. Okay, so Hadamard matrix. Well, a Hadamard matrix is a square matrix that's unitary, and it has the additional condition that all of the entries have the same complex modulus. So right here I have an example of a 4x4 Hadamard matrix. Rho here is any complex number of modulus 1. It doesn't matter, you'll end up getting a unitary matrix for any such complex number. Now I'm using a slightly different definition than the historical definition. So the historical definition of a Hadamard matrix is not a unitary but an orthogonal matrix, meaning it's not scaled to have norm 1. And it has entirely real entries. So basically just plus and minus 1s is the classical definition of a Hadamard matrix. Now I will not make a distinction between real and complex Hadamard matrices here. That's the historical distinction, but I will just call them Hadamard matrices. Let me comment here that there's this still open problem about what sizes of matrices can you have a Hadamard matrix. So it's fairly easy to show that if you have a real Hadamard matrix, so only plus and minus 1s, then the dimension of the matrix has to be divisible by 4. That's a necessary condition. The open question still is whether that's a sufficient condition. So it's a long-standing open problem that if you have a dimension divisible by 4, is there a real Hadamard matrix? Okay, so the context in which Hadamard matrices appear, well, there's probably many more than I'm even aware of, but a few of them that I've listed here. For analysis on fractals, which is really my motivation. The Fuglede conjecture, which is a long-standing problem that I won't say anything about here. Multi-channel filter banks, coding theory, quantum physics, you name it, there's probably an application of Hadamard matrices. Okay, so to put this into context, if you take the standard n by n Fourier matrix, that is a Hadamard matrix. Well, again, complex, but I won't make that distinction. If you take the standard Fourier matrix, that's one of these matrices. And I want to know about the spectral properties of this matrix. Well, it's a very easy calculation to show that if you take the standard Fourier matrix and you raise it to the 4th power, you get the identity. And what that means by the spectral mapping theorem is that the eigenvalues have to be fourth roots of unity. So 1 minus 1, I and minus I. Now that doesn't tell you anything about whether all 4 of those numbers are eigenvalues, and it doesn't tell you anything about the multiplicities. It just says that if you have an eigenvalue, it has to be one of those 4 numbers. Now it turns out that the actual multiplicities of those eigenvalues were determined by McClellan and Parkes in 1972, and it's quite a long, tedious calculation. It's not complicated, but it's fairly tedious to actually show what the multiplicities are by actually just calculating specifically eigenvectors for all of the eigenvalues. Okay, so to set the stage here for what I'm interested in, so let's look at the 5x5 Fourier matrix. That's a 5x5 Fourier matrix. If I permute the columns in some way, I'm going to now change the spectrum. I'm going to change the eigenvalues. So this, I already know what the eigenvalues are by McClellan and Parkes, including multiplicities. For this one right here, I'd have to recalculate because I've changed the eigenvalues by permuting the columns. Now, we've actually calculated the eigenvalues for the permuted 5x5 matrix. But the question is, what if I permute in a different way? Do I have to recalculate it every time? Well, In essence, yes, and in some sense, no, is the idea I want to get across today. So just a bit of notation. So a Hadamard matrix, again, has all of its entries with complex modulus 1 over square root of n if it's an n by n matrix. I will assume, for convenience, that the first row and first column has 1s in it. That's called a dephased form of a Hadamard matrix. And given any Hadamard matrix, I can always put it in dephased form by pre and post multiplying by a diagonal matrix, probably different. And so that will change the spectrum in general, but for my purposes, I'm going to always consider dephased Hadamard matrix. And the lower right corner here, which is not ones, is called the core. So that's where all of the action occurs in what we're trying to do. Okay, so ignore the top part here and just look at the middle statement right here. It says if you have two matrices with the same trace, then they have the same spectrum. And sigma here means the eigenvalues of the matrix, including multiplicity. Now, if you don't look at the hypotheses and just look at that statement, you say, well, that's wrong. And of course it is. You can have two different matrices with the same trace, different eigenvalues. So this is the remarkable thing from what we've discovered, is that if you have two Hadamard matrices of some common class, and I've listed them there, but let's put that aside for the moment. If you have two Hadamard matrices of some common class, then the trace being equal, it actually implies that the eigenvalues are equal, including multiplicities. Okay, so what are these classes of Hadamard matrices for which this statement is true? Well, we were able to show it's true for 4x4 Hadamard matrices. We were able to show it's true for 5x5 Hadamard matrices. And we were able to show it for a very small class of larger Hadamard matrices. And I'll explain what this means here as we progress. All right, now let me comment here before moving on that these three classes for which we can prove this is true are all quite small compared to the class of all Hadamard matrices. And basically what makes this work, in particular with the 4x4 and the 5x5 case, is that we can write down all such Hadamard matrices. That is to say, we can write down all 4x4 Hadamard matrices. We can write down all 5x5 Hadamard matrices. We cannot write down all 6x6 Hadamard matrices. There's a paper that came out 6 or 7 years ago, roughly, that we call the catalog, and it was basically almost a complete description of all known Hadamard matrices. And even that is incomplete once you get beyond dimension 5. It's an incomplete catalog. So a natural question is, well, can we say the same thing about 6x6 Hadamard matrices? It'd be nice if it were true. I suspect probably not, but we have no way of knowing because we just can't write them all down. And so any proof of this type of statement would have to not rely on actually knowing what all of them are. Okay, so let me go back to the permuted Fourier matrix case. So the third class here that I mentioned that we can prove this result about the spectrum is symmetric permutations of the n by n Fourier matrix. So if I take the Fourier matrix, the n by n Fourier matrix, and I permute the rows and I permute the columns, in general that will change the eigenvalues and their multiplicities. So the class here is I want to consider only those permutations of the n by n Fourier matrix which ends up being symmetric. That is, its transpose is equal to itself. not its adjoint, its transpose without the complex conjugate. Okay, so suppose I have a Hadamard matrix, which is some permutation of the n by n Fourier matrix, and suppose that it is symmetric, that is to say its transpose is equal to itself. Then there exists a unit in Z mod n, and there's a permutation that depends on that unit in such a way that the spectrum of the permuted Fourier matrix I'm given is equal to the spectrum of this particular matrix. Now this permutation matrix here has a special form. I'll explain what that means in just a moment. But the point of this says, the purpose of this says is that if I have any permutation of the Fourier matrix, which is symmetric, and I want to know what its eigenvalues including multiplicity are, well, I just have to match it up to one of these. And how many of these are there? Well, there aren't many. So basically, if I just calculate all the eigenvalues for all matrices of this form, I'll have described all possible eigenvalues for any matrix of this form. Okay, now what is this, this permutation matrix here, that special notation? What I'm doing is I'm taking the columns of the Fourier matrix, and I'm permuting them by multiplying the index of the column by m. So the jth column of Fn goes to the m times j column under this permutation. And I need that to be a permutation of the columns, and that's why I need m to be a unit. It needs to have a multiplicative inverse in Z mod n. Okay, so again, if I want to know all possible eigenvalues, including multiplicities of all such matrices of this form, I just need to figure out what they look like for these matrices, and I have a complete description. Okay, so how do we do that? Well, if I have such a matrix, that is to say, if I take the n by n Fourier matrix and I permute the columns via this manner, then I can actually calculate the multiplicities of I can actually calculate the eigenvalues, and I can calculate the multiplicities I have the table on the next page here, and I'll bring it up in just a moment. Let me point out before I get there that it turns out that any matrix of this form has the same property as the standard Fourier matrix, in the sense that this matrix raised to the 4th power is the identity. So that tells me the eigenvalues have to be 1 minus 1, I, and minus I without doing any work whatsoever. Then the question becomes the multiplicities. And the way that we describe the multiplicities is by looking at the trace. And the trace of such a matrix as this turns out to be a Gauss sum. So we take the trace of this matrix. It turns out that it has this form. It's a Gauss sum. And thankfully, Gauss actually tells us what the values of those Gauss sums are. So we can calculate the trace of this matrix without, we just look at what Gauss tells us, what the value of that sum is. Okay, so here's the long table. And you don't have to absorb that in any way. The point is simply that we can have a complete description of the eigenvalues of that matrix, including multiplicities, and it depends on various things. Well, let me take a step back here. It turns out that the value of this Gaussian sum depends on several things. It depends on what m is modulo 4. So 0, 1, 2, or 3 modulo 4, that determines a different value for this Gaussian sum. And then there are these so-called Jacobi symbols that appear in the value of the Gaussian sum. And so all of these columns here to begin with are a description of the modulo class, or the residue class of the dimension modulo 4 and m modulo 4, and then these Jacobi symbols that have different possible orders, values. And then once we know those parameters, we can tell you exactly what the eigenvalues and multiplicities are for that matrix. So we have, going back one more time, we now have a complete description of what the eigenvalues and multiplicities are for all possible matrices that look like this. And then by this theorem that says we now have all possible descriptions of eigenvalues and eigenvectors of matrices that look like that. Okay. So what about the other two classes for which we can prove this trace implies spectral equivalence result? Well, 4x4, I skip all the details here and just tell you that we can write down a table that gives us what the values of the eigenvalues are. So the entries in this table here with this row, that goes back to, let me go back to the, yep, right here. So this is an example of a 4x4 Hadamard matrix. It turns out every 4x4 Hadamard matrix has this form up to permutation of columns in some way and permutation of rows in possibly some other way. So every Hadamard matrix looks like that. 4x4 Hadamard matrix looks like that. And so if we have a 4x4 Hadamard matrix, it's got 1s, -1s, and then row that appear as the entries, and then the 1/2, the scaling factor out in front. And depending on whether it's symmetric, non-symmetric real, non-symmetric non-real, you get different values for the eigenvalues. And so we have a complete description now of the eigenvalues for a 4x4 Hadamard matrix. The case that I find more fascinating is the 5x5 case. Now again, I mentioned earlier that we have a complete description of the 5x5 Hadamard matrices, and this is due to Uffe Hagerup. And his result says that if you have a 5x5 Hadamard matrix, then it has to be some permutation of the 5x5 Fourier matrix. So that is to say, any 5x5 Hadamard matrix has to be the Fourier matrix, 5x5 Fourier matrix, with the rows permuted in some way and the columns permuted in, again, potentially some different way. Now, in particular, what this means is that the 5x5 Hadamard matrix must have all of its entries which are fifth roots of unity. And that really greatly simplifies the class of 5x5 Hadamard matrices. Okay, so we have some elementary number theory that helps us out here. So if we have a 5x5 Hadamard matrix, then as a consequence of some elementary number theory, that Hadamard matrix must be a Latin square in these 5 symbols. So here omega is a fifth root of unity, so we have the powers of omega. We must have that the matrix, the 5x5 Hadamard matrix, must be a Latin square, or as I like to say, a Sudoku puzzle. That's what we call them nowadays. A Sudoku puzzle in these 5 symbols. So you can't just put fifth roots of unity in a 5x5 matrix at random and expect to get a Hadamard matrix. Another thing another consequence of some elementary number theory is that if we have two 5x5 Hadamard matrices and their traces are equal, then their diagonals actually have to be equal. So that's not quite saying that the eigenvalues have to be equal, but they have to have the same entries along the diagonal, possibly in different positions. Okay, so basically the point is we now have a complete description of all 5x5 Hadamard matrices, and we know a lot about their structure. Okay, so how do we proceed from here? So I'm trying to prove that if two Hadamard matrices have the same trace, then their eigenvalues are the same. That's what I'm trying to prove. Well, this tells me if I have two Hadamard matrices, again 5x5, and their trace are equal, then their diagonal entries are the same. And so what I now do is I simply do an exhaustive search of all possible Hadamard matrices, which have the same diagonal. And if I can say that they all have the same eigenvalues with multiplicity, then I get the result I'm after. So that's the game we play. So what we do is we start, for example, we start with a Hadamard matrix which has all 4 of its diagonal entries in the core. So remember I've got 1s on the first column and 1s on the first row that I'm ignoring at this point. So suppose I have a Hadamard matrix 5 by 5. This is the core, and suppose all 4 entries along the diagonal are the same. It could be any of the remaining 5th roots of unity. I don't know, but they're all the same. Now, because of the Sudoku condition, how can I fill out the remaining entries of this matrix? Well, there's lots of different ways of filling out this matrix to get a Latin square, and I just simply write them all down. And then I start eliminating certain possibilities. So it turns out that if you take all the 5th roots of unity, put them into a 5 by 5 matrix in such a way that you get a Latin square, that still may not be a Hadamard matrix. You still may not have orthogonality. So there's additional structure required about where those roots of unity appear. And so some of these possibilities we can eliminate because of the orthogonality condition of the Hadamard matrix. And so of the remaining 3, I just have to figure out, do they have the same eigenvalues? And that's what we do. We prove that the remaining 3 possibilities end up having the same eigenvalues if they have the same diagonal entries. So combining that with this says if I have two 5 by 5 Hadamard matrices with the same 4 diagonal entries on them, they have the same eigenvalues, which is the theorem I'm trying to prove. So we do this for all possibilities. 4 of a kind, 3 of a kind along the diagonal, that's actually not possible. 2 pair along the diagonal, we go through all possible cases of that. 1 pair and 2 singletons, we go through all possible cases like that. And then 4 singletons, that's actually not a possibility for a 5 by 5 Hadamard matrix. So it's basically just an exhaustive search of all possibilities, and then we prove that if they have the same trace, they have the same eigenvalues. That's why we can't do this for 6 by 6, because we're using the fact that we know what all of them look like in the 5 by 5 case. It's an exhaustive search proof. Okay, so here's a table that just simply lists all possible spectral values of a 5 by 5 Hadamard matrix. And of course, you don't have to absorb that in any way. The point is simply that we can write them all down. And so we now know what the eigenvalues of any 5 by 5 Hadamard matrix looks like, again, in D-phased form. Okay, so I mentioned at the beginning that we're really interested in these Hadamard matrices that appear in the context of Fourier analysis on fractals, and that's what I want to go to next in the remaining few minutes. We've sort of observed, this is really just an observation, that in the things that we're trying to do, we have what I would like to call a fast fractal transform in the spirit of the theme of our talks at this conference. So this is just a way of describing the context in which I'm in. So what I have going on here is I have the usual Cantor middle third set that I'm going to construct, not in the typical way where you take the unit interval, remove the middle third, take the remaining intervals, remove the middle third, and repeat ad infinitum. I'm actually going to build it sort of the other way from the ground up rather than top down, up, bottom up. I'm going to take the point 0, and then I'm going to divide by 3, which of course leaves that fixed, and then I'm going to add 2 and divide by 3. That'll get me 2/3. And then I'm going to take those 2 points and I'm going to repeat that process. I divide by 3, add 2, and divide by 3. And if I repeat that process, this iterated function system, I'm going to develop a bunch of points that are irregularly spaced, that if I continue this process and then take the closure at the end, I get the middle third Cantor set. So what I want to do is I want to build, let me take a step back here. I want to build a Fourier basis for this collection of points. And what that turns into a matrix, all of whose entries are exponentials. Here I haven't normalized, but preferably I would like this matrix to be an orthogonal matrix, which means I would like these exponentials on this collection of points to be orthogonal. Now in the middle third Cantor case, that's impossible. That's an impossibility. So the next best thing is, can I get this to be an invertible matrix? Well, that I can do fairly easily by building up through the iterated function system. But what I want to point out here in conclusion is that if I take this n by n matrix, all of whose entries are these exponentials, I can permute the columns in such a way that I get this nice factorized form. Now what that means is, if I think of this H sub n as being a Fourier transform on this collection of points, I can reduce the number of computations I do by roughly a factor of 2 in the same way that the fast Fourier transform does. So the way that the fast Fourier transform operates, the way I think of it, is you take the standard Fourier matrix, you put all the even indexed columns first and all of the odd indexed columns second, and then you get these this block form. So if you replace Hn with Fn, you'd have Fn minus 1, Fn minus 1, and then you have these diagonal matrices. And so you can avoid doing the computation with this block and this block. You can do that computation just once instead of doing it twice, doing this computation and that computation just once, and that's where the reduced number of calculations occur in the fast Fourier transform. So in our fractal case here with the Cantor set, if we're building these things from the ground up, at every scale we can induce what I like to call a fast fractal transform from scale n, relate it to scale n minus 1, and reduce the number of calculations, which I thought was kind of cute. It's not, again, it's really just an observation, but I thought it was pretty neat. So I'll stop there. Thank you for your attention.
Any questions? Oh, I'm sorry. You're doing everything in detail.
Yes. No. Well, we didn't look. Yeah. I don't know. I haven't really even thought of it. I suspect not. I would be shocked if it were true for 6x6 Hadamard matrices. Yeah, I skipped one slight technicality there. I'm restricting my attention only to integer frequencies. If you allow non-integer frequencies, it may be possible. Anyway, go ahead. Well, okay, so you mean this stuff here, or are you talking about the? Yeah. Okay. So so we're taking the cue from Jorgensen and Peterson, the way that they have this Hadamard pair that they talk about. So what you do is you start with these contractions here, and then you try to find these digit sets that when you put into a matrix that looks like this, you get a unitary matrix. That's what Jorgensen and Peterson are after. Now, the way that this works is if you want the same number of generators for both of these iterated function systems. So if you allow yourself to take more generators for this, what you get is you get a tall, skinny matrix, which could be a frame. And in fact, my student John Hare was working on that earlier on what happens if you do that kind of thing. You do get frames. And in fact, if you take 3x, 3x plus 1, and 3x plus 2, so you take all possible digits for scale 3, and you form this kind of matrix here, you get a Parseval frame, well, a tight frame, if you don't scale, like I'm not scaling here. You get a tight frame at every scale. Now the frame bound blows up, which is why you can't take a limit the way that I would like to. But still, at every scale, you get a really nice exponential frame.
She obviously asked a brilliant question.
Yeah, that's right.
Following up on that, the open problem then about frames for L2 of the 1/13 set is still open.
Yes, that's correct. As far as I know, that we still do not know of an exponential frame for the middle third Cantor set. That's a great question because my student John, in his poster session, is going to talk about Fourier series without the existence of a frame. You can express functions on the middle third Cantor set in terms of a Fourier series, just not in terms of a frame.
Well, it was a great talk.
Thank you.